Welcome to ECE595, Statistics 598, Machine Learning 1. Today we are going to talk about lecture number 36 on defending strategies. So before we go into the technical details, let me give you an outline of what we want to do today. If we recall what we have studied in the past two lectures, you realize that we have talked about several attacking strategies, both in the linear space and also in the deep neural network settings. So today we are going to talk about defending all these adversarial attacks. In particular, we are going to talk about three classes of defending strategies. They are the pre-processing strategies, introducing randomness, and adversarial training. Now, I want to warn you that if you go and read a paper on adversarial attack tonight, you are likely to find a method that may or may not be within these three classes of strategies. And indeed, this field is rapidly evolving. And so these three classes of strategies, they are just representing the strategies that we know so far. And I promise you that there will be many new strategies coming out today, tomorrow, and the day after. The methods that we're going to talk about will be all based on deep neural networks because these are what people have been implementing. The challenge is not the principle, it's actually the implementation, because you can imagine when you have a deep neural network, you really need to get access to the network parameters in order to attack if you're talking about a white box attack. We are going to talk about deep neural network defenses because we want you to understand what is happening outside. We are also going to talk about there are holes in all these defense strategies. In particular, we are going to introduce you a technique called obfuscated gradient or gradient masking. And finally, in this lecture, I'm going to give you some very biased opinion on this topic in general. Adversarial attack, which direction should we go, and what would be the open problems in this area, and what are the more challenging problems in this field in general. So here is the outline of today's lecture. We'll be spending half of our time talking about the three classes of defending mechanisms. They are the pre-processing methods, the adversarial training methods, and also the introducing randomness methods. And then we are going to talk about the limitation of these current defenses. Specifically, as I said, we're going to talk about a method called the obfuscated gradient or gradient masking. And then we're going to ask the question, can we actually launch attack in physical space? Something that you have seen in the introduction of adversarial attack, but we want to go a little bit deeper into asking whether it is actually possible to do a physical attack. I also want to share with you some experience with collaborating with our sponsors in doing research about studying attacks in real social media today. And I want to give you some opinion of what are the challenges out there when we go to the second part of this lecture. So to start with, I want to talk about three types of defense strategies. Let me start by talking about the pre-processing strategy. Okay, so imagine that you have a data point X, and what you want to do is that you know that the data point X has been perturbed. So this is a perturbed data, and it's a very noisy data. So what you want to do is that before you send this X to your classifier, you do want to do some kind of pre-processing of your data X. So here's what is going on. Let's say you have an X, which is a perturbed data, and you want to send it to a classifier F. Before you send it to F, let's say that we want to introduce another operation called G, so that the G can do some kind of cleaning up of your data before you send the data to the classifier. And so if you can do this processing properly, then perhaps any noise that is happening in your X will be gone after you apply the G. So the main idea of pre-processing is really to take this input data and then pre-process it and then send to a classifier. And so you can see that there will be a pre-processing unit, and then ultimately the thing that you're going to classify will be F composite with G applied to X. And there are many ideas that you can do this kind of pre-processing. For example, you can do denoising. Let's say X is a noisy observation, and then you apply an image denoising algorithm, then you can denoise all these attacks. So this is one possibility. The other possibility is to project the perturbed data onto some kind of image manifold. You can also treat it like a denoising, but on the other perspective, you can just say that I want to perturb my data onto any manifold that I want it to be. Pictorially, what do we mean by pre-processing? Well, let's imagine that you have a clean data, which is here. The clean data is perturbed by your adversarial attacker. It will go from this point to here. Now, this black line is called the decision boundary. This decision boundary says that after this perturbation, my data point will go to here, and so it becomes misclassified. The denoising or pre-processing that we are going to apply is going to project this data point onto some kind of manifold. And this is called the manifold of the image because it's really defining the space where the image should look like. Now, this is a very abstract concept, but you can imagine that what would be the space of image? Would it be just a bunch of numbers? Probably not, because you have objects, you have texture patterns, and you have edges, you have color. These are living on a low-dimensional subspace rather than living in the ambient high-dimensional space. And therefore, these data points, they will be likely to live on some kind of manifold, although we don't know what the manifold is. But when you do the denoising is indeed trying to project the perturbed data onto this invisible manifold. Let me give you a few examples of this pre-processing idea. The first idea is called the input transform, introduced by Guo et al. In 2018. And this title is called the Countering Adversarial Images Using Input Transformation. It was published in ICLR in 2018, and you can find the archive paper in this link. So the basic idea of this method is that they are going to solve an optimization as follows. In this optimization problem, X is the noisy input, and the optimization variable is Z. So they're trying to find a Z such that this overall objective function can be minimized. Now, in this objective function, you have two terms. The first term says that I'm going to subtract X from Z, and so that will be the difference between your optimization variable and your input. There is also another term called 1 minus X. This is a mask. And so X is an array of Bernoulli random variable, which is either 0 or 1 for every pixel. And so you're going to randomly select a subset of pixels, and you're going to measure the deviation only at those locations. And then you are going to create a penalty term. This is called the total variation norm of a vector. And specifically what total variation means is that a TV norm on a Z would basically be D1 of Z, one norm plus D2 of Z of is one norm. Now, what is D? D is a finite difference operator. You have D1 and D2 that accounts for the horizontal and also the vertical finite difference operator. In order to implement this, what you do is that you take this image and then you shift the image to the left or to the right by 1 pixel, and then you subtract the difference. So this is a finite horizontal finite difference. Now, you can also do the vertical finite difference by taking the shift vertically. Then you can do this difference, and then once you do take the former, subtract from the later, then you can get this d2 times z. And then the one norm just says that you're going to take the absolute value. So this is one type of total variation, and you can have many different forms of variations if you read the literature. So basically what this optimization problem says is this. I have an observation z and it is noisy, and I want to find an optimization variable z such that the distance between z and x will be minimized. However, I don't want it to just become minimized, because if I only minimize it, then I will just get the z exactly equal to x, because then the solution would be the best solution such that this norm is 0. But because you have this lambda times the total variation of z, you say that you are not happy with only minimizing this term. You also want to minimize the other term. And the other term says that I do not want to have lots of variations in an image, because this is a finite difference operator, or in other words, it is a high frequency operator. If you take this finite difference operator, you're going to get most of the edge information out. And so if it is very noisy, then this total variation will become very big number. And therefore, total variation is trying to promote the smoothness of your data. And therefore, when you're trying to solve this optimization problem, you are guaranteed to get not only that your z will match with x, your output image should also become a little bit smoother. So in the paper, they also introduced the other types of input transformations that are not necessarily just this total variation minimization. They've also introduced this JPEG compression technique. If you read the paper, they have introduced 2 or 3 more different input transformations. The bottom line message here is that if you give me an X, I want to apply some kind of image denoising or some kind of other type of processing like this JPEG compression technique in order to clean up any perturbation that I have in my X. So here is just a slide summarizing what is total variation. I really want to point you to the original paper by Rudin and Osher back in 1992, which really is the first paper that introduces total variation. So if you're interested in our group's work, you can go to here. You can see that we also have a total variation solver based on the idea of augmented Lagrangian. Pictorially, what you have is this. Suppose this is a clean image, and then here is your noisy image. You can apply a total variation solver, then you will be able to do some kind of denoising. And so you can see here, if you have adversarial attack pattern going on in your noisy image, and after total variation, most of the background, they will become smooth. And so a lot of these adversarial attack patterns will be gone. In the same paper, the author talks about how are you going to train your deep neural network in order to handle these kind of input transformations. So they say that you need to educate your classifier about the input transform. Here are 2 types of training procedures that you can find. The first type of procedure is called a baseline vanilla training procedure, which says that you only give me all these clean data points, and then I'm going to train a model and classify. So that's the baseline. Here is the second form of training, where you really insert the transformation into the classifier, and then you input the data, you send it through the transformation, and then you train the classifier. Now, here you can also try to think about what would be the testing strategy. The testing strategy is to is to have an adversarial attack that will be applied to your input image, and then you are going to get a perturbed image. Then you're going to transform using either a total variation denoising or stuff like that, and then you apply it to your model. The model can be this improved version or the vanilla version, and if you read the paper, they will have discussions on how each model will perform. In this input transformation, we notice that the input data that they use here, they are the clean data. There is really no adversarial pattern during the training. If you introduce any adversarial pattern into this training, the method would become something else. It's called the adversarial training technique. And I want to decouple the two by talking about two different sets of slides so that you are not confused about which one versus which. Now, certainly, when you are doing the actual implementation, you can combine both. You can have adversarial training plus those transformations. Let me also talk about another example of input transformation type of defense mechanisms. This is also a pre-processing technique. It's proposed by Liao et al. In 2017. The title of the paper is called Defense Against Adversarial Attacks Using High-Level Representation Guided Denoisers. It was published in 2017 on Archive, and indeed they won the NIPS 2017 challenge. And so what is the idea? The idea is fairly straightforward. You go to the previous set of slides, you see that they are introducing a total variation denoising algorithm. And so this group of researchers, they ask, what if we just train a deep neural network denoiser within the classifier procedure? Will it be able to better train this denoiser? And so what they do is that they start with a vanilla classifier, and then they are going to send a pair of clean and noisy images to the same network, and then they're going to pull the features, and then because one is using the clean data, the other one is using the noisy data, and certainly the features extracted by the two networks will be different. And so they set a loss, and they train the denoiser. So exactly what they do is the following. Imagine that you have a CNN1 convolutional neural network 1, and then you have the same convolutional neural network. And then you send this original image, and then there is an adversarial image to the exact same neural network. So because these are the two exact same neural networks, you get their feature maps. So you can pull the features out. Okay, you can pull the features out, and in this example, they're just looking at the second last layer of the network, which is this kind of features. And so if you have an input image which is original, then you can get a feature that looks like this. But if you're sending an adversarial image, then the input will look like this. And certainly there's a difference between the two, because for the same network, if you send an adversarial image, the feature will of course look different than the clean image. And so there is a loss which is measuring the difference between these two features. And so they're going to send this loss into another deep neural network denoiser. So this is a denoiser. It has certain structure. It could be a UNet structure, or it could be a residue denoising structure. So they're going to feed this loss into the denoiser, and then their goal is to train this denoiser. So the difference between this approach and the total variation denoising approach is that this denoiser is really customized or trained to help this specific CNN to do the classification work in the presence of this type of adversarial attack. And so they show that with this approach, you are able to improve the performance significantly, and that's how they can win the NIPS challenge. The idea of using feature representation can be summarized using the equation as follows. So you have a classifier F which takes an input data y, and then you want to map it to a label x star. So here is the typical loss function. Let's say you're using the L2 loss, then this will be your error. Now, in their approach, what they do is that they are going to send. Okay, so F is not the classifier. So F is actually the denoiser. Okay, so F equals to denoiser. Okay, so you send your y through a denoiser, and then you measure with respect to the clean data. So what they do here is that they send the same y to the denoiser, but they are not just comparing the x directly, they're comparing the features extracted by the network. Okay, so now they're comparing the features, and so this is a comparison in the feature space, and so this is what they call the high-level representation guided denoiser, because they're really looking at the high-level representation and not just at the pixel level comparisons. In my opinion, this is very similar to Jeffrey Hinton's knowledge distillation. That was a very famous paper published in 2015, which I encourage you to take a look. And so back in 2015, the idea was to compress the deep neural networks. And so they're also using this kind of feature transform to measure the loss. There is another paper that would be interesting for you to take a look. This is by Zhang et al. In 2018. And this paper says that if you pull the features and you compare the difference of the feature maps, that will also serve as a very, very good perceptual metric that can tell you what is the similarity between two images. All right, so now let me move on to talk about introducing randomness as a type of defense mechanisms. The idea of introducing randomness is that you have a perturbed data, and when the data comes, I want to introduce some kind of uncertainty in my classifier so that you, as a hacker, you may not know exactly what is the state that I am operating at. And therefore, I will be able to defend more of your attack than before. And so the example would be like this. You can have a suite of classifiers, but you don't know which one that I'm going to use. Or I can randomly flip a few pixels or mask out some pixels and then solve a matrix completion problem. Or I can just randomly move around the pixels so that the attack is distorted. Okay, so what would be the example? Let's go to here. This is the first example proposed by Sear et al. In 2018. The title is Mitigating Adversarial Effects Through Randomization. It was published in ICLR in 2018. And the idea is actually quite simple. Suppose you have an image, xn. What they propose is that they are going to randomly resize the image. Now, by resizing, I really mean that in the digital computers, you make the image bigger or smaller. In addition, they are going to randomly pad the image, meaning that they are going to move the image left or right, up and down, with some random padding. And then finally, they are going to select one out of that, and then that would be the image that they take, and then they just send to your classifier. So when you try to introduce this kind of randomness, then the classifier that we'll be using is, of course, will be more immune to any kind of attacks, because the attacks is really focusing on attacking this image. If you make it bigger, smaller, left and right, then the gradient locations may be changed. And so in many cases, then the classifier will be immune to these distortions. The second example in the randomization approach is proposed by Prakash et al. In 2018, and the title of the paper is Deflecting Adversarial Attacks with Pixel Deflection. And this is published in 2018's CVPR, and the idea is also extremely simple. And so what you do is that you go to your image and then you pick a pixel. Okay, so let's say here is your image. You really pick one pixel, and then you create a neighborhood. In your neighborhood, you have a lot of pixels. Then you replace your pixel by another pixel in your neighborhood. Okay, so here is the algorithm. The algorithm says that I'm going to pick a PI from your image I, and this U stands for the uniform distribution. So uniformly, I will pick a pixel and then replace it by something else. Now, what do I mean by something else? It would be this N would be your neighboring pixel, and it's coming from this neighborhood, and you're also trying to draw a sample uniformly from the neighborhood. And then your output image at location PI will be replaced by the pixel value located at NI. And so this is the algorithm. And then they do it for a few pixels, and they show that you can effectively mitigate the adversarial attack. The third example of randomization is proposed by Taran et al. In 2019. The idea is to defend the adversarial attack using this thing called a randomized diversification. This is published in 2019's CVPR, and the idea is to construct a suite of K classifiers, and each classifier has a key. And so what you're going to do is that you're going to pull some features, for example, the last layer before the soft max, and then there is an aggregation unit which will know the key, and then the key is used to combine the features. So let me give you an example first, and then we'll come back to talk about more of these properties. So let's say you have a image that it comes in, and then you will have a lot of these transforms. So the DCT transforms. Okay, so the DCT transform stands for the discrete cosine transforms. Now, when you do this discrete cosine transforms, you will also have different classifiers at different stages of your DCT coefficients. Okay, so when you apply a DCT, you apply a discrete cosine transform. If you send this image into the discrete cosine transform, you will be able to get the high frequency and also the low frequency components. So you can pretty much think of decomposing the image into different components, and then you have different classifiers for different components. And so you're going to get different features out of each classifier, and then you are going to concatenate all these features together, and then you are going to form an overall classification result. And so the randomness can be introduced at here. You can introduce you can say that I'm going to do some random multiplication. I'm going to select some pixels out from here, and then this information can be fed back to this aggregation unit, so that you know which unit to add, which unit to skip. Because you are the defense mechanism, you know what you have, you know the key, whereas the hacker doesn't really know what the key that you are using, and therefore this presents a pretty reliable method of defending the attacks. So the attack does not know the key, and therefore you have advantage over the hackers. In my opinion, this method is okay for black box attack. But if you're really doing a white box attack, that means the hacker also knows the key, then this method becomes unclear whether it will be able to defend. And if I am a hacker, then what I would do is that I will assume I know the distribution of the key. Now, this is something that I may or may not be true, but suppose I do know the distribution of the key. I don't know exactly which key that you're using in this particular instance, but I know that your key you have several keys, and these keys, they are uniformly distributed across the space. Then I can just take the average of all these keys, and they will attack your average. Now, I may not be as effective as if I know the key. However, I can still attack your average case. And in many, many situations, attacking your average case, and if I can increase my attack strength by a little bit, I usually can attack your system. And so this is some potential drawback of the ensemble method. All right, so we have gone through two types of defending strategies, and now let me also talk about the adversarial training, which is the third type of defense mechanisms. One of the most famous papers in this domain is by Madry et al. It's called the Towards Deep Learning Models Resistant to Adversarial Attacks. That was published in ICLR in 2018. And the problem is to solve a minimax optimization. Now, let me explain this notation. Here you have a loss function L, and theta would be your network parameters. X would be your input data, and Y would be your label. Delta is a perturbation that you're going to add to the input data. And so when you look at this expression, it will be the loss of your network by putting a perturbed data point. So this is your adversarial attack data point with the original correct label. Now you're measuring the loss. How about this delta? You define a space of S. This is the set of all the possible deltas can live, and you're taking the maximum of all the loss. And so you're saying that among all these perturbations delta, I'm going to pick the worst one so that my loss will be maximized. So if you recall what we have talked about for the maximum loss attack, this is really trying to find an attack that can maximize your loss in the set of S. And then outside this maximum operation, there is an expectation. The expectation is taking over all the possible training samples X and Y from the training set D. And so I want to average over all the X and Ys. So that will account for my training set. Finally, outside, I have a minimization over theta. So among all the worst cases, among all the average worst cases, I want to find a theta such that this overall thing can be minimized. So in other words, I really want to minimize the worst case scenario for the attack. Now, how are you going to minimize this problem? This is an extremely hard problem to minimize. Typically, what you can do is to solve an iterative minimization procedure. In other words, you are going to first fix your theta, and then fix your X, fix, and Y. Of course, X and Y, you have to take the average over a training set. But you fix a theta, and then you are going to find a delta that can maximize the loss. And in order to solve this problem, what you really need to do is to really attack your model, your current model. And so you need to solve this maximum loss attack during your training procedure. And once you have computed this loss, then you're going to minimize this theta. So you make a gradient descent step on the theta, and then you go back and you train your theta, and you go back and you recalculate the attack, you find the worst case attack, and you go back and you update your theta. Now, certainly you can see that in this formulation makes a lot of sense, because here what you're doing is to minimize the worst case attack. And so if you can solve this problem, then clearly you can really defend against the worst case. However, the price you need to pay is the computation, because you need to solve this problem iteratively, and each iteration you need to come up with all these attacks. The explanation by Madry et al. Says that if I have a data set that are located at this, if you don't do anything, then this is your decision boundary. And the decision boundary can be very sensitive to certain perturbations. If my data point is here, I have a data point that's living here, and if I draw the L infinity norm ball around this data point, then you can clearly see that I will become misclassified as the other class. With adversarial training, what you will get is a different decision boundary like this. And so in this case, you are more you will be more resilient to the attacks. As I described before, there are lots of practical considerations for the adversarial training. And so in order to solve this problem, you need to simulate all these worst case scenarios. And that is, you need to compute this loss function. And this requires a lot of deltas that you can draw from your set S before you can attack. And so you also need to compute the average. And for example, given a dog image, you need to perturb the image many times in order to get to the worst case scenario. And this one dog image, you may need to have maybe a 10 times more data. And so if you are talking about an image net data set, which is 1.28 million images, you do a 10-fold adversarial training, that is 10 times more examples. However, this 10-fold adversarial training is still not guaranteed to be enough, because you can think that a dog image, you have at least 200 pixels by 200 pixels, and so there are so many variables. And what would be the minimum number of adversarial examples that would be required for you to reliably train this model? This is an open question, which we don't know. And so if you read the paper, what Madry et al. Have shown is that they are only able to demonstrate the results on smaller data sets, for example, the MNIST data set or the CIFAR-10 data sets. Scalability seems to be a very challenging issue for these adversarial attacks. You can do something beyond adversarial attacks, and there are lots of follow-up papers on this adversarial training procedure. This is one of the more recent paper. It was published by Wen et al. In 2019. This is a Photoshop face detection method. So the problem says that this is the manipulated photo, and then what they want to do is that they want to detect what has been changed with respect to the original photo. So here's the original photo. So you can see that the face of this person is changed to the manipulated photo. And this subtle change is very not noticeable if you just show this image to a person. So what they're doing is that they go to the Photoshop, and then they write a lot of scripting files, and then they are going to mimic the attacker in the Photoshop space. So suppose I have this image. Normally, what would be the possible perturbations that an attacker can do in order to perturb the image, and everything can be done in Photoshop. And so they really do this adversarial training by scripting the Photoshop. And so once they have enough this adversarial examples, then they train a detector to detect the changes. So this is another example of adversarial training. There are other advantages of the adversarial training. So in 2018, this group of researchers they show that there are some benefits of adversarial training. They say that they are not certain about exactly what is the reason, and they call it an open problem in adversarial training. Now, let me describe the two phenomena, and perhaps that can inspire you something. The first phenomena that they observe is that the loss gradient, that is the gradient of your loss function, in the input space seems to align very well with the human perception. And so what it says is this: you try to train. For example, this is the MNIST data set. You try to train using the standard procedure, and then you look at the gradient with respect to the input. This is the gradient, okay, and certainly this is the adversarial. This is not the adversarial training. And then you try to train the exact same model using the adversarial examples, using the minimax problem. Then what you can see is that the features that are being extracted, they are much more meaningful. Now, how do we interpret meaningful? To me, it's more like the input image that you have. For example, if you look at here, this is a bird image. You do get some edges of the bird. This is an insect. You do get some edges of the insect. And so these adversarially trained models seems to be able to extract more meaningful features than a standard training protocol. The second phenomena that they observed is that the adversarial examples exhibit salient data characteristics. So here is an example. This is the original image, is a MNIST data set, a digit 4 and a digit 9. And then if you try to train with the standard protocol, this is what is being seen by the, if you want to attack this standard protocol, then the perturbation would look like this. Okay, so this is the perturbed data that will be able to fool your classifier. Now, if your classifier has been adversarially trained, then you can see that in order to fool the same classifier, the example that you need to use would look like this. Now, if you look at this, if you ask any human, the person would say this is already a 7. This is a digit 7. Is unlikely to call it as a digit of 9. If you send this image to a human, you ask him or her, you ask, what do you see in this image? And the person will say this is still 9, although when you send this image to the classifier, that standard protocol classifier would say that this is 7. For adversarially trained classifiers to fail, you do really need to send an image that really looks like the object that you want it to become. This is another example. Here is an airplane. And then if you use a standard trained network, the perturbation that can succeed in attacking this classifier is still like an airplane. However, if you use the adversarially trained classifier in order to succeed in the attack, you really need to turn it into a bird. So that creates some very interesting question of what is being done by this adversarial training. Maybe it's beyond just the robustness. Maybe there's something else that we are not aware of. All right, so we have gone through 3 classes of defense mechanisms. And in these 3 classes of defense mechanisms, I've also introduced a lot of examples of how do you defend. Now, in the following half of the lecture, what I want to do is talk about the limitation of these current defenses. And specifically, I want to introduce a method called the obfuscated gradient attack, which will be able to attack the pre-processing and also the randomness defense mechanisms.